Hello students, welcome back. The final topic here in lesson 10 is section 7, additional topics in normality. And frankly, I'm not so sure whether this is really a worthy topic to discuss in abstract algebra 1. Here we go anyway, and I may later decide to take this one away, but for now, let's talk about it. First, simple group. A group is called simple if it has no proper non-trivial normal subgroup. And most of the time, a simple group has small group size, but some simple groups can be really large. For example, any ZP for prime number is a simple group because it has no non-trivial proper subgroup at all. You see, prime numbers are divisible by 1 and itself only. And if prime is really huge, then of course that's a simple group. And then as for non-abelian examples, I don't know, it's really hard to find out. One thing I do know is this. Alternating group of n greater than or equal to 5 is simple. And this is humongously important in abstract algebra 2 for field theory, as a matter of fact, because there we'll have to prove that polynomial equation of quintic or higher cannot be solved algebraically. Cannot be solved in the algebraic means alone. That means using only addition, multiplication, subtraction, division, power, and radical only. And there, we have to use the property of alternating group of n greater than or equal to 5. But other than that, I don't see any use of those, especially in abstract algebra 1. So let's not worry about these. And as for simple groups of some humongous size, there are some monster simple groups discussed in our textbook. So if you're interested, look at those. And if I remember correctly, there are some well-known simple groups such as ZP and AN and things like those, and then there is exactly 26 others, named as A to Z, number of alphabet. Anyway, normality under homomorphism. So normality is preserved on the homomorphism. To be a little bit more precisely, it should be called epimorphism because we are doing everything an image, not on the target. But this is something we already discussed in section 3 of this notebook or section 3 of lesson 9. And then maximal normal subgroup. The normal subgroup is called maximal if there is no proper normal subgroup of G that properly contains M. So here, naturally, it is called maximal, especially in terms of the subgroup structure or set inclusion. And the normal subgroup M of a group G is maximal if and only if factor root G of M is simple. Yeah, okay, but I don't think it is worthy of class time to prove this. It's no, never mind. Yeah, if this somehow becomes necessary, I'll prove it, but I really doubt it. I mean, in abstract algebra 2 maybe, but abstract algebra 1, highly unlikely. Commutator subgroup. This may be an interesting topic. Let A and B be elements of a group G, then this element, AB times A inverse times B inverse, is called a commutator. So the subgroup GC generated by all commutators of G is called the commutator subgroup. So what does this commutator does? Well, if this thing is trivial, then A and B commute. But if it is not, then it forms a subgroup called commutator subgroup. And then what we are going to do is we are going to cut it down. it'll turn out the commutator subgroup is a normal subgroup. And then if you cut it down and make a factor group, then it's an abelian group. The factor group is abelian, you see? And this is commutator. If this is E, then A and B commute. But if they don't, then you can force them into trivial by cutting it down. So the coset of this commutator, and then if you consider those, then never mind. It's getting too complicated without actually writing anything. And as for writing something, I don't know, it's going to be too much of an effort. So I'd rather stop here. Just remember the result at this time. Commutator, yeah, this kind of thing is called commutator. And then a subgroup generated by all these called commutator subgroup. And it turns out commutator subgroup is abelian. Commutator subgroup is normal. And then if you consider the factor group, then it turns out abelian because we just simply killed off all the commutators. Okay, all right. That completes some miscellaneous topics of lesson 10. And it's quite likely I'm going to end up skipping section 7, but at this moment I'm a little bit less certain, so I did discuss a little bit. That's why I'm going to stop.